Okay, the goal for this lesson is to learn how to find specific solutions to indefinite integrals. Now, so far, you should know how to solve basic integrals and get what's called a general solution. That is, that solution that includes the plus c. So that's called the general solution because it applies for all functions that you take the integral of, but it isn't actually very useful. In your algebra classes, you've never seen a function that has this undefined plus c. So, like I said, by now, you should know how to take a simple indefinite integral and get a general solution, but just as an example, let's say that f of x equals 2x squared. And so you take the indefinite integral and call the answer to the indefinite integral, we'll call that capital F of x. So that's going to be indefinite integral of f of little f of x dx, which is going to be the integral of 2x squared dx. Okay, take this integral and it becomes 2/3 x cubed. 2 is a little messy, plus c. So we have our general solution like this. Two-thirds x cubed plus c. Like I said, the specific solution actually tells us what the plus c is. But in order to get a specific solution, you need to know the value of the function, capital F, both its x and y coordinates. So you need one pair of coordinates that this function satisfies. And then you take that pair of coordinates, call it x0 and y0, and substitute it back into the general solution. Then you use algebra to solve for c. So let's say we also knew that f of 0 is 3. Well, that means that when x equals 0, then y is 3, or f of x, capital F of x, is 3. So you take these numbers, substitute it back into here, and you say say that f of x, which is 3, equals 2/3 times, well, x, which is 0, cubed plus c. All right, well, 0 cubed is 0, and so a little bit of algebra tells you that tells you that c is equal to 0. C is equal to 3, rather. Then you substitute the value of c back into the general solution in order to get the specific solution. So we got a value for c here. We have a function that includes c. Just take that 3 and replace the c back here. So your final specific solution is that capital F of x is equal to 2/3 x cubed plus 3. That is your specific solution. And you can do this because this value of c is true for all of the function capital F. It's not just true for this particular pair of coordinates. This is just one pair of coordinates that happens to lie on this function. And once we solve for that c applies to the entire domain of the function. All right, so let's just briefly review what we learned last class, which I've already applied, actually. Oh, and so, sorry, one last point. This final version of the function, with the 2/3 x cubed and the actual value, an actual number for the constant, this is called a specific solution. All right. Moving on. Since the first step is getting the general solution, all of that knowledge that I taught you last class in order to find general solutions has to be applied in that first step. So we're going to take our integral properties. If we see two functions added together, we're going to distribute the integral across those two functions. If we see any constants, we're going to factor that outside of the integral symbol. And once we're done with that, we should get something that looks like this side of one of the integral identities. And then once you have this side, you can get rid of the integral symbol and the dx and just by applying one of these identities. All right. A typical problem that expects you to solve for the specific solution will start off like this. You'll get the name of a function, usually a capital letter, not always though, and that's going to be the integral of some function of x, dx, or maybe a function of time or whatever. So you'll get something you have to take the integral of, and the key additional piece of information that you get is this: the value of the x-coordinate of the function, in other words, the 1, so that's going to be your x0, and the y-coordinate, the corresponding y-coordinate of the function. That's your y0. All right, so going back to the general method, step 1, find the general solution. Okay? First up, take your integral properties. We've got 3 different things added together, so we spread the integral, we distribute the integral across those 3 terms. So what we end up with here is that g of x equals integral 9x to the 4th dx plus integral of 3x squared dx minus integral of 15 dx. Okay, so that's the application of the distribution of the integral. Now we factor all of these constants out, the 9, the 3, and the 15. Okay, don't forget this integral dx is the same thing as saying integral of 1 dx, which is the same thing as saying x to the 0 dx. Alright, so now we should have something that looks like one of our properties, and indeed all 3 of these terms are x to the n. The n's different for each term, but that's okay. So we bump this number up by 1 and also copy it down to the numerator. That gets rid of the integral symbol and the dx. So this becomes 9x to the 5th over 5 plus 3 times x cubed over 3 minus 15x, and then at the end of all of this we put a plus c. Oh yeah, and all of this is still capital G of x. Alright, do a little bit of simplification and then we're done with our general solution. Alright, so that's your general solution. Step 1, done. Step 2, substitute our x0 and y0 into the general solution. So, here's our known x0 and y0 up here. We're going to take the value of 5, and that's going to be g of x. That's going to equal, okay, wherever we see an x, we drop a 1 in there. And now you see that we end up with a function where the only unknown is c. At this point, you could give this to anyone who's taken an Algebra 1 class, and they could solve for c. So let's just go ahead and do that. Do the simplification. 1 to any power is 1. And then clean things up over here a little bit. add 14 to both sides, subtract 9/5. And you can either subtract the 9/5 over to the other side, or you can switch the positions of the C and the 19, and by subtracting C from both sides and subtracting 19. Either way, you'll end up with, in the end, this. Let's see, 19 is the same thing as 95/5. Okay, a little bit of math, a little bit of arithmetic here gives us 84/5 is C. Okay, now take this, just substitute it back into here, and then you're done. So, our overall specific solution is g of x equals, we just copy this stuff down, 9/5 x to the 5th plus x cubed minus 15x plus, now instead of the c, we just copy this number, 84/5. And yeah, that's a 4 right there, not a 9. Alright, so that's how to do a simple example of finding a specific solution. Let's take a slightly more complicated example of this. And let's see, I have a grand total of 5 examples. So now we got this sine function here, and we know that sine of pi, that q of pi is equal to 2. All right, let's go ahead and figure out how to do this. Step 1 is to find the general solution, just like we did in the last class. So, in order to do that, we don't have anything added together, so we don't use this property, and then we do have a constant here, so we can take the constant and move it outside of the integral. Alright, now that we've got sine of r all by itself, that looks like sine of x dx, except instead of wherever we have an x, instead we have an r here, so that's okay. Integral of sine is negative cosine. And for our general solution, don't forget the plus c. Now, actually, there is one little thing I forgot to mention here, and that is that whenever you have a sine function, you have to specify whether it's in degrees or radians. So as part of the original problem statement, I should have said r is in radians. Otherwise, this pi thing doesn't make a whole lot of sense. Okay, so we got our general solution. Now, let's move on to the next step, which is solving for the c, and that means taking our known value of x and our known value of y and substituting that into our general solution. So our known value of x is pi, and our known value of y is 2. So this means that 2, now let's switch colors, a little late for the 2. 2 equals negative 12 times the cosine of pi plus c. Alright, hopefully you remember what an unadulterated cosine function looks like. If not, here's the basics. Remember, it goes up and down like this. This is a 2 pi right here, and this is pi right here. So that means that cosine of pi equals negative 1. Okay, so You get 2 equals negative 12 times negative 1 plus c. That means 2 equals 12 plus c, which means that c is negative 10. Okay, so we got a solution for c. Now, we just take this and substitute it back into here. So for our final solution, no, that is not a reference to the Nazi final solution. It's just the solution we get in the end. I am not a white supremacist, but anyway, q of x equals negative 12 cosine of r minus 10. So we took the c, substituted into here, and that gave us this as our final solution. By the way, on that statement about me and white supremacy, pay attention to the not part. I said I am not a white supremacist. Make sure that that doesn't get all over the internet. Anyway, so something a little bit more applied here. Acceleration, which is a, is equal to 2. Velocity as a function of time is equal to the integral of a with respect to time. And the object is initially at rest. Well, when something's at rest, that means that its velocity is 0, and the initial time is 0. Right? Whenever you start a stopwatch, it better have the reading 0 on it, otherwise you forgot to clear the stopwatch. Alright, so what these words mean is this initial value. Alright, so v of t is equal to the integral of a with respect to t, and so let's go ahead and do step 1 of our problem-solving process, which is to take the indefinite integral and get a general solution. A is equal to 2, so that means wherever we see an A, we can put in a 2. And this is the same thing as if you need to substitute in the t to the 0, that's fine. If not, don't worry about it. If you're sufficiently quick at this that you can avoid doing that, then go ahead and save yourself some time. Integral of t to the 0 is t to the first power over 1, so this is going to be that. Okay, so we got our general solution, but that's not good enough. We can get a specific solution here. So v of 0 equals 0, so that means that we have the coordinates x equals 0, y equals 0. Let's switch colors here. So we get 0 equals 2 times 0 plus c, and since this whole thing becomes 0, that means that 0 equals c. Okay, take 0 equals c, plug it back into here for our third and final step. That means that v of t equals 2t. Right, because adding 0 is just nothing. Alright, so that's your specific solution. Alright, let's say we've got something a little bit more complicated. This is acceleration is equal to negative 3 cosine of t. And we have v of 0 equals 0, and we also have that x of 0 equals 3. Find the specific solution for x of t. Now, you do need to know one additional thing in order to solve this, which is a little bit of what's called kinematics. That's the study of how objects move in physics. And what that the first lesson in a calculus-based kinematics course is that you start with position, and if you take the derivative of position with respect to time, you get velocity. And if you take the derivative of velocity with respect to time, you get acceleration. Well, if derivatives go from position to velocity and velocity to acceleration, then that means integrals go in the opposite direction, because remember, derivatives and integrals are opposite operations. So that means that velocity is equal to the integral of acceleration with respect to time, and that position is equal to the integral of position with respect to time. So what this problem is asking us to do is take an integral, find the specific solution, and then do that again. So we take the integral of acceleration, we use that to get velocity, along with this one known point here, and then we take, this should be integral of velocity. There we go. And then we take velocity and we integrate that again, and then we apply this specific solution in order to find this known point in order to get a specific solution for position, otherwise known as x. All right, so basically we're just doing this process twice. It's like a